Hello viewers, welcome back to my channel. In this session, I shall be discussing the banker's algorithm. This banker's algorithm comes under the topic deadlock avoidance under the module called as deadlock. So from the beginning, if you recall the topics that I have been explaining, very first session for this module was regarding the introduction to deadlocks and the necessary conditions for the deadlock to occur in a system. Then I started telling you about the deadlock detection methods and using the resource allocation graph and the deadlock recovery methods. Next is deadlock avoidance method. So if you have to compare this deadlock detection with deadlock avoidance, see normally what no you are going to use this deadlock detection method. Definitely even with this we can come to know whether the system can be in the safe state or not by seeing whether the resources requested by the different processes can be accepted or not by the system. But that is okay if you have very less number of instances for a resource. But if you have more number of instances for a particular resource, then we need to go to the next topic called as deadlock avoidance. So in this particular algorithm, the system also checks whether the system can be in the safe state after granting the request made by the different processes. The banker's algorithm is based on what this algorithm is actually used in the banks before sanctioning a loan to a person. So normally if a person is requesting for a loan amount from the bank has to sanction the loan to that person, keeping in view that the other account holders who have got their accounts in that bank, they deposited money. Okay, if at all any point of time, if all account holders, if they withdraw the entire amount also, the bank should be in a position to make them allowed to withdraw their complete amount as well. The loan which is requested by some X person can be granted. That means the bank should be in a safe state that without affecting the actual account holders that are having their money deposited in the account. So before sanctioning the loan to the person X, this condition is checked and only then the request for the loan can be granted or not based on the resources that are available in the bank. With this introduction, we shall move on to the problem here, and the numerical can be asked for 8 to 10 marks, and you are given this kind of question here. Okay, the problem statement is like this. I'll just read out the question. Using Banker's algorithm, find how many resources of the type A, B, C, D are there. What is the need matrix? Is the system in the safe state? Determine the safe sequence. So all these three parts you have to find out. Now we'll start working on the numerical. What is given in the problem statement? First I'll explain you. And moreover, I wanted to tell you that this Banker's algorithm, there are two different algorithms under this heading. One is the safety algorithm. The other one is the resource request algorithm. So there can be a numerical on safety algorithm or there can be a numerical on resource request algorithm. So the first in this session I am going to explain a numerical using the safety algorithm. That's why I've written here in bracket safety algorithm. But the main title is Banker's algorithm, and this comes under the heading what called as deadlock avoidance. So deadlock avoidance, deadlock prevention, these methods are different from deadlock recovery. Recovery is simply like what if at all you have to take an analogy, the person has suffered from some illness and you are giving the treatment to recover from that particular illness or disease. That is deadlock recovery. But when it comes to deadlock avoidance, you are taking care here so that the person will not get affected with illness at all. That is what is the precaution taken here in the system, in the operating system, so that the system should not suffer from the deadlock, or there should not be any deadlock occurring in the system. Before the deadlock occurs, the system is trying to take all the possible precautions. So definitely we require those precautions, we require those measures. We cannot take the risk here. See, normally deadlocks, if it is happening in our regular day-to-day activity in the laptop, so it is fine. We can definitely restart the system. We can ignore. That's why there is a heading called as deadlock ignorance also. But suppose if the deadlock occurs in systems, in real-time systems, if at all, if you see in the aircraft systems, in that particular system is also what completely equipped with computers, and that system which is completely taking care the control of the airplane which is flying, and if deadlock occurs, just see the impact. So that cannot be taken. That is a risk. So definitely the system has to take certain precautions to avoid deadlock. In the hospitals also, if the patient is admitted in the ICU and the computer which is taking care of, because there are so many equipments that are connected for the treatment of that person, and if that computer faces this deadlock situation, then just imagine what will be the impact there. So all these real-time systems, we cannot take the risk. We have to have some measures so that deadlock can be avoided. So this is what is the banker's algorithm. First one is the safety algorithm, and the second one is the uh, resource request algorithm. So with this introduction, I shall start telling you about what the in numerical. I shall start explaining a numerical on this particular banker's algorithm, and I'll be first explaining using the safety algorithm. The numerical will be asked in this manner. You are familiar with allocation and available, but not with maximum. So let me explain to you the first what is given in the problem statement. In the problem, what is given is the different instances of the resources that are already allocated to the processors. Maximum is first, let me tell you about A, B, C, D. A, B, C, D are the resources here. It can be anything. A can be printer, or B can be plotter, CPU, memory. Like this, it can be any resource. So what is given is the instances of each of these resources are mentioned under these headings A, B, C, D. Normally, for a process to complete the task, the process knows that maximum it may require certain instances of the resources. Maximum. So maximum is what? For example, you take process P1. P1 says that maximum I may need one instance of resource A, seven instances of resource B, five instances of resource C, and zero instances of resource D. That is, I don't require any instance of D, and already assigned by the system is only one instance of the resource. So how much is the pending? Pending can be always calculated with what? The need matrix. So here in the solution, first thing is you have to start writing the values for the need matrix. All this, why I am saying the word matrix is, you can see here, okay, this is a two-dimensional array allocation. Maximum, it is a two-dimensional array. Need will also be a two-dimensional array, whereas available will be a one-dimensional array. Now you start writing the values for the need. So as I said, need is what? If a resource needs maximum these many instances, allocated is only this much. So what is the pending? That means remaining instances of the resources. So for that, very easy, you can always write need equal to maximum minus allocation. Need of I equal to maximum of I minus of allocation of I. So if at all you have to come, so I'll write the formula also better here, maximum minus allocation. Now look here, P naught is there. Now don't start doing anything with the available, just fill the values for what the need matrix. What is that you have to do? Maximum minus allocation, and also while writing the values, you have to subtract log 1 to 1, A 0 minus 0. So 0 minus 0. So I'll just write here, one second, let me write even the kind of resources. A is B, A, B, C, D are the different kinds of resources. This one is what? Need, which is nothing but maximum minus allocation. Okay. Now subtract and get the value for the need matrix. Available you're not supposed to get maximum. 0 minus 0. Okay, 0 minus 0. 1 minus 0. 1 minus 1, sorry, 2 minus 2, 0. Okay. So this one you have completed. Next, we'll check with the P1. 1 minus 1, 0. 7 minus 0, 7. 5 minus 0, 5. 0 minus 0. Okay. So this way you have filled the values for the need for P1. What about the need for P2? P2 also you can do in the same manner. 2 minus 1. How much? 1. 3 minus 3. 0. 5 minus 5. 0. 6 minus 4. 2. That completes for P2. Next is P3. Right? 0 minus 0. 6 minus 6. 0. Then 5 minus 3. 2. 2 minus 2. 0. Come to the last process here, 0 minus 0, and then 6 minus 0, 6, 5 minus 1, 4, 6 minus 4, 2. This is what is asked here, need matrix. Also, I wanted to tell you the very first question, how many resources of the type A, B, C, D are there? How many resources of type A, B, C, D are there in the system? It's total. exactly, sorry, initially in the system, how many instances of each of these four types of resources are there. How to calculate? Easy. What you have to do is you add up the column values for allocation with what, with the values of the available. That will give you the total instances of all the different types of resources. If you add here, you will get 2, 9, 5, 8, 9, 10, 4, 8, 9, 10, 11, 12. Okay, this is what, this is the, after you add up the columns of the allocation matrix now available in the system. That means the system, after assigning these many instances to different processes, still the system is left with 1520. Suppose if we add with 1520 with already the allocation, then you will get 3, 14, 12, 12. So we can say that totally in the system there are 3 instances of A, 14 instances of B, 12 instances of C, and 12 instances of D. So this is what the answer to the first part. How many resources of the type A, B, C, D exist in the system? So very simple, that part you can easily complete. Once you do that, you move on to the next question. Next part in the question is the system in the safe state? How to check whether the system is in the safe state or not? You need to use these steps here, which I have mentioned. These steps, what? These steps are a part of what? The safety algorithm. So start working one by one with the process P naught. This is what we have started also. Now for process P naught, let us see. Okay. Need of I equal to maximum minus allocation I. This step already we have done. Okay, for process P1, need value is 0, 0, 0. So for what we can do is, when we carry out for all the processes, this first step we need not do every time. The values are already filled here. You can directly start with this second step, need of I less than or equal to available. If it is true, then available equal to available plus allocation of I. So that I'll be explaining. First, need of I. Need of I here, I is P naught. So when we are taking P naught, what is the value for the need? Need is 0, 0, 0, 0, less than or equal to available. Available is 1520. So why we are doing this step is, definitely the system says that I may, in this case it is different situation. It does not require any instances in future also, but still we have to follow this procedure. So if this is equal to what, lesser than or equal to the available, it will check, because the system is having only these many instances, it has to check what is the need for process P naught, whether it can satisfy or not. In this case it is true, yes, it can be satisfied. So I can write here, it is true, less than or. Then immediately what is that you have to do? Available equal to available plus allocation. What is available? 1520. Plus allocation of P naught is 0012. Okay, normally don't write like this. Give space between numbers, because we are not writing this as one number. It belongs to what, different instance, different resources. 1520 plus 0012. Now why we are adding here is, once P naught makes use of whatever is given here, in this case need is 0. Suppose whatever is given here, once it makes use of this, it will return whatever was allocated initially to P naught. 0012 will be returned, and it will be added with what? It will be added with the available instances. So in this case it is how much now? 1, 5, okay, 2 plus 1, 3, and 0 plus 2, 2, 1532. So what I'll do is, I'll update the value here. The new value is 1532. So now the system is having 1532, and P naught can complete its job. So P naught has completed its job, and the system is back with whatever resources P naught has taken earlier. Now let us check with process P1. Okay. Process P1, what is the allocated value? Process P1 is having allocated 1000, and the process P1 has, what is the need? 0750. So we have to check whether 0750 is less than or equal to the updated value of allocation, because this is the current value for available now. we have to check with what? The current value of the available. 0 is less than 1, 7 is not less than 1. Sorry, 7 is not less than 5, 5 is less than 3. Sorry, 5, in this case we check for P1. 0 is less than 1, true, but next number you see 7 is not less than 5. 5 is also not less than 3, 0 is less than 2. So even one resource, if it is not satisfying, it is not lesser than or equal to the available, then you cannot make this system P1 to complete its job. So we say it is false here, and if it is false, then P1 is not able to complete, it is in the waiting state. P1 has not completed, so I'll put a cross here. Next we'll check for process P2. P2 is having what? P2's need is 1002. We have to check with the available value 1532. You can see here 1 less than or equal to 1, 0 less than or equal to 5, 0 less than or equal to 3, 2 less than or equal to 2. It is true. So here no problem. This process P2 can complete its job. So process P2 will be what? Given with 1002, and it will complete its job and it will return whatever was initially allocated. 1354 will be returned. So that's why we have to write down now available equal to available plus allocation of I. Available is what? 1532 plus P2 allocation is 1354. It is returning back to the system now because it has completed its job. So what is the value here now? The new value for available is 1 plus 1, 2, 5 plus 3. Yes, 5 plus 3, 8, 3 plus 5, 8, 2 plus 4, 6. 286. 2886. Okay, 1 plus 1, 2, 5 plus 3, 8, 3 plus 5, 8, 2 plus 4, 6. So now the current next value, that is the updated value for available, is 2886. So this way you keep on updating the values also in the available matrix. Now this also has completed its job. Let us check for process P3. Process P3 need is how much? 0020. Check with what available values? 2886. Yes, it is true. It can be satisfied by the system, and then it will return whatever was allocated. 06 process P3 0632, it will return, and then it will get updated with the. So first let me write the available value here. So available is 2886. Then it will return whatever was allocated initially, 0632. Fine. And the new value for the available is 2, 14, 8 plus 3, 11, 6 plus 2, 8. So let me update now the new value. New value is 2, 14, 11 and 8. Fine. After that you have one more process. So P3 is also able to complete its job without any problem. Next is P4. Let us check for process P4 now. Process P4 need is how much? 0642. Is it lesser than or equal to available? 2, 14, 11, 8. Yes, it is true because you can see all these numbers 6, 4, 2 lesser than. So it is true here. If it is true, add available equal to available plus allocation. 2, 14, 11, 8 plus what is that allocated? 0014. Okay. Once you add, you will get 2, 14, fine, 11 plus 1, 12, then 8 plus 4, 12. So you are now, the new value for available is 2, 14, 12, 12. So this also I'll just 2, 14, 12, 12 is the available value. Now after you complete this, you should go back to the previous process which was not able to complete its job. That is process P1. Now let us see whether process P1 can complete its job. So we'll be moving back to this process P1 now. P1 request was what? 0750. Now the system is having 2, 14, 12, 12. Is it lesser than or equal to 2, 14, 12, 12? You need to check. 0, 7, 5, 0. Yes, it is true. Now the process P1 can also complete its job, and it will return whatever resources that were allocated earlier to process P1. What was allocated? 1, 0, 0, 0. So the new available value is 2, 14, 12, 12 plus 1. Where is that 1? 0, 0, 0. Once you add 2 plus 1, 13, 14, 12, 12. Okay. Once you add, you are getting what? 3, 14. And you just see at the end, whatever. Okay, fine. This is the new current value for available. Now you can update the available value. It is what? 3, 14, 12, 12. You yourself can verify whether you have carried out correctly or not, because initially you have determined this total number of resources in the system 3, 14, 12, 12. Now you can see the system is once again back with this 3, 14, 12, 12 after all the processes completed their job and they have released the resources. So this is how you have to, now we can say yes, the system is in the safe state. So do not skip this part. Here in the question, is the system in the safe state? That is the third part of the question. Yes, the system is in the safe state. You have to write like this. Yes, the system is in the safe state. Why we are saying in the safe state is we were able to complete all the process. We were able to, the system was able to make all the processes get completed their jobs. There was no deadlock happening in the system. That's why we say the system is in the safe state. If it is in the safe state, what is the order of processes in which these processes got executed? So first P0 got executed. Okay. First P0 got executed. The safe sequence you can write like this. Safe sequence is, this is the fourth part of the question. P0 you can write in angular brackets or any. P0, P1. No, P1 did not get executed. First P0, P2, P3, P4. And then process P1. So no doubt you had deferred the execution of process P1, no problem. Our ultimate aim is to see that there should not be what? A deadlock occurring in the system. And we have seen that with all whatever resources that were available, we were able to manage and all the processes completed their job, and this is the safe sequence. So this is how you have to carry out the banker's algorithm. Here the algorithm is the safety algorithm. We have to check here whether the system is in the safe state or not. The next algorithm will be slightly different from this. It is called as the resource request algorithm. Even there also you have the initial steps, okay, different. Rest you will be once again following all the steps of the safety algorithm to arrive at the solution. So if you find this session useful, please like, share and subscribe to my channel. Thank you. Bye bye. Take care.